Welcome again to another lesson on sequences and series. Last lesson we had a look at geometric sequences, and now just as after looking at arithmetic sequences we looked at arithmetic series, today after looking at the geometric sequences we're going to have a look at how we sum together geometric series. Before we do that though, as you can probably guess by now after 100 plus videos on this, there are some warm-up questions to get you in the mood and get you in the zone, so here they are. 4 to try, although questions 3 and 4 do link to each other. Have a read of these, press pause. If you have a worksheet in front of you, try them on your own and press play on the video when you want to see the answers. Okay, so let's get going and have a look together at warm-up question 1. So this is going back to year 12 binomial expansion. So we're asked to find the first 3 terms in ascending powers of x, so the powers of x getting bigger, of this binomial expansion 2 plus kx to the power 6. So this one here, the first 3 terms at least, of 2 plus kx to the power 6. First of all, the first term is always 6 choose 0. Different teachers will teach it in different ways. I always think of the first one as 6 choose 0, which is actually 1 anyway, but this, in my opinion, helps set the pattern up. 6 choose 0. The first term is always beginning to be to the power of the overall bracket, so 2 to the power 6, and the second term, in this case of kx, will be to the power 0, same as that bottom number here. Now as we move on, this bottom number increases by 1 each time. The power of the first term decreases by 1 each time, so power 6 becomes power 5. And the power of kx, the last term, will increase by 1 as we move along. And the third and final term we need to work out will be 6 choose 2, 2 to the power 4, kx to the power of 2. So all we need to do now is to use a calculator to actually evaluate these terms here. So 6 choose 0, I'll show you how to do this on a calculator. Whoops, that's not what I wanted to do. So we press 6, where we do shift and the divide button, on this class was at least, then 0, press equals, we get 1. Anything to power 0 is just 1, so all we need to concern ourselves with is 2 to the 6, which just gives us 64. So the first term is just 64. Next, we've got 6 choose 1 multiplied by 2 to the power 5. So if we work this one out, 6 shift divide 1. That's 6 choose 1 multiplied by 2 to the power 5. We get 192. So that's going to be 192 kx. And the third term we need to work out, 6 choose 2, 2 to the power 4. We can actually save some time by just going back and altering what we've got here. So I'm going to change that 1 to a 2, like so. We'll get 240. So that's 240 k squared x squared. So those are the first 3 terms. Part B throws a bit of a curveball at us. Part B asks us to work out the x cubed term, essentially. We're told the x cubed term is minus 20. So we need to actually evaluate the x cubed term here. So it's just the next term after this one. So we've got to the squared term. The x cubed term, we've gone 0, 1, 2. The bottom number now will become a 3. So we've got 6 choose 3. Then it's 2 to the power 3, because that power's going down by 1 each time. And then it'll be kx cubed, and we're told that's going to equal, well, the coefficient of it, is going to equal negative 20. So the coefficient, if you're not sure, just means the number in front of the term. So if the coefficient of the x cubed term is minus 20, that means this thing here is going to equal minus 20 x cubed. So what we can now do is actually work out what 6 choose 3 times 2 cubed is. So if we see here, this is what we'd actually get. You'd get 160 for this. So this is 160, and then kx all cubed gives us k cubed x cubed. and that equals minus 20x cubed. But we're just interested in the value of k. We don't need to worry about the x, so essentially we can just cancel off the x cubes on both sides. Afterwards, we can divide both sides by 160, and if we do that, we see that k cubed will be negative 20 over 160, and that simplifies down to be negative 1/8. So therefore, k is going to be the cube root of negative 1/8, which turns out to be minus a half, which your calculator can tell you. So cube root of minus 1/8. Go away, McAfee, honestly. Okay, so cube root. So get the right button, Mr. Bailey. So shift that one, that's what we need. So minus 1/8. Get negative a half, like I say. So that's what k is. Therefore, we've done the first question. Let's have a look at question 2. Here we've got a curve with this equation, y equals 10x squared plus 3x. We need to use differentiation from first principles to find the value of the gradient of the curve when x equals 7. So differentiation from first principles tells us how to calculate the gradient from first steps. It's always the same procedure. The gradient function, dy by dx, is the limit as h approaches 0 of the expression f of x plus h minus f of x on its own all over h. So here what we need to do, we need to let y equal f of x, just so we can fit it into our definition of differentiation from first principles. So if y is f of x, then f of x plus h will just be what y is if x is swapped for the input x plus h. So let's do that next. And sadly, we need to write this every single time, lim h going towards 0. So f of x plus h will be 10 lots of x plus h all squared, plus 3 lots of not just x, but now x plus h. And then if we subtract away f of x, need a longer fraction line because this is quite a mouthful, we're going to subtract away 10x squared plus 3x. And all of that, again, is over h. This can go in brackets if you want to as well. It's optional. So it's just a bit of a slog, but we're going to get there. Just trust that you'll get there. It might take a while, this, but it's fine, because although it takes a long time sometimes, the marks aren't actually that hard to get, as long as you're patient. This one here, expand out x plus h all squared and multiply this whole thing by 10. So I'll just do this and I'll colour code it so you can see where it's all coming from. So x squared is x squared times by 10, that gives us 10x squared. If we're squaring a binomial, we double the product of the two terms. So x multiplied by h is xh. Double that gives us 2xh. Multiplied by the 10 on the outside, that's going to give us 20xh. Then finally, h squared is, well, h squared times by 10 gives us 10h squared. Now, we can do the plus 3 lots of xh. So expand this out as well. So 3 times x is 3x. 3 times h gives us 3h. Then we can subtract what we have here. So minus 10x squared is obviously minus 10x squared. minus positive 3x gives us minus positive 3x, like so, and we still didn't have a fraction line long enough because it's such a long thing to do. So all of that still is over h. Now, as awkward as this looks, what we can do now is simplify an awful lot of stuff. So we have 10x squared here, minus 10x squared there. So we can cancel that 10x squared with this minus 10x squared. Similarly, we have positive 3x here, minus 3x there. So we can cancel those off too. So now what we can do is just look what we have left and divide through by h. So we've got the limit of h goes towards 0. So now we can just think what we're going to have left after dividing through by h. So if we divide through by h, 20xh divided by a h, the h's will cancel, that'll just leave us with 20x. 10h squared divided by h squared divided by h will leave us with just a h on the top, so that gives us just 10h. And finally, 3h divided by a h, that h will cancel this h, so we're just left with a 3. So now you can see as h shrinks to 0, 10h will shrink to 0. That'll just leave us with 20x plus 3. And that's almost our final answer, in fact. However, we want to work out the gradient of a curve when x equals 7. So we just sub in when x equals 7. So when x is equal to 7, the gradient when x equals 7, this is optional notation, you don't need to remember this, it's just my way, which is valid, of writing the gradient at a particular value of a variable. So the gradient when x is equal to 7 equals 20 times 7 plus 3, which will just give us 143. That's the second one done. Let's have a look at number 3, and therefore number 4 as well. So here we are. We've got a bathtub full of water which is being drained by removing the plug. The volume of water in the bath 1 minute after removing the plug was 100 litres. The volume of water in the bath 1 minute 40 seconds after removing the plug was 40 litres. The volume of water in the bath v litres, t seconds after the plug is removed, can be modelled as a linear relationship between v and t. Find an equation linking v and t. So we're told it's linear, so we should be thinking of maybe sketching a straight line graph, but of course it's not x and y in this case, it's v and t. So which is the independent variable? Well, t is independent. The volume of water in the bath depends on the time. We can't go back in time by changing the volume of the water, so time is completely on its own page. So time is independent, therefore the independent variable goes along the x-axis on the bottom, and v goes vertically. So v is going to go vertically, t goes horizontally, like so. So we can start by sketching the axes out here. Next we can think, well, what's the first thing we're told in this question? Well, we're told t's in seconds, so that needs to be noted. The first bit of information is, when we've got 1 minute after it's been drained, the volume is 100 litres. 1 minute is 60 seconds, so 60 seconds, 100 litres. We can plot that point on our sketch. 60 and 100. The next bit of information is that after 1 minute and 40 seconds, the volume's 40 litres. So 1 minute and 40 seconds is 100 seconds in total. So 100 seconds and 40 litres is our second point. So we can add that to our sketch like so. Now, because it's a linear relationship, we need to fit a straight line going through these 2 points like this. Our problem now is working out the equation of this purple line. Well, we know 2 points, so the best step, in my opinion, is to work out the gradient. So the gradient is the change in v, normally it's a change in y, but it's a change in v in this case, divided by the change in x normally, here it's a change in t. So the volume goes from being 100 down to 40. So the volume's gone down by 60. Whereas time has moved along from 60 seconds to 100 seconds. So time's gone on by 40 seconds. So simplify this or use your calculator. For gradients, minus 3 over 2. We can now use the idea of y equals mx plus c. Any straight line can be expressed as y equals mx plus c. So in our case, our y is v. Our gradient, we've worked out, is minus 3 over 2. The x is actually t in our case. Then the c we can work out where it crosses this v-axis. All we need to do is just substitute in a point we know. So we can choose either this point or that point, it's up to you. I'm going to choose here to substitute in 60 and 100. When the time's 60, we know the volume of water was 100 litres. So 100 equals minus 3 over 2 multiplied by 60 plus c. So 100 minus 3 over 2 times 60 gives us minus 90. Then add c. So therefore, the intercept is 100 plus 90, which is 190. So therefore, we can say, for volume, our y, if you like, equals a gradient, minus 3 over 2. So minus 3 over 2, if you want to, you can write as a decimal. So I'm going to say minus 1.5 t plus, in our case, c, which is 190. So our c here is 190. So I could have said minus 1.5t plus 190. I'm going to just go for v equals 190 minus 1.5t. And that's our relationship, which could have been written in more than one form, but in the form of y equals mx plus c, or even in our case, c plus mx. That's a relationship which will do us. We're now going to use this to answer warm-up question 4. So, for the linear model in question 3, find the initial volume of water in the tank. Well, going back to what we had, here's what we had from before. The initial volume is just the volume when the time is 0. So that's just interpreting what we did from question 3. So the initial volume is 190 litres. So before the plug was pulled, we had 190 litres of water. The time taken for the bath to completely drain, well, it's drained when the volume is 0. So we just sub in 0 for v. So 0 equals 190 minus 1.5t. Add 1.5t to both sides. 1.5t equals 190. Therefore, the time for it to drain is 190 divided by 1.5. Let's see what we get here. So 190 divided by 1.5. We're going to get three significant figures at least, about 127 seconds. So just over 2 minutes of a bath to drain. That's possible. Fairly quick draining. I think mine has too much fluff or hair, but you know, each bath's different. 127 seconds, about 2 minutes. That is possible. If you've got something like 5 seconds, be double checking your answer. But 127 seconds, that seems fair enough. I'm just going to say here, that's been rounded to 3 sig figs. Finally, suggest a reason why this model may not be suitable. There's a few things you could put. The two main reasons that come to my mind are as follows. If you've got a suitable alternative, let me know, and I'd comment back to say if I think it's fair enough or not. So as long as you're not stupid with this interpretation, this is only a 1 marker, chances are you get the mark. The 2 main suggestions I have are, first of all, the bath may become less wide at the bottom. Most baths do. Okay, so it won't drain in a uniform fashion. The rate of drainage won't be constant, it just never is. That might be because the bath might become less wide at the bottom, or you could just say the bath might not have an equal width throughout. It might not have a uniform cross-section, would be another way of saying the same thing. And for those physicists out there who know something about water pressure, you could say the water pressure will decrease as the water drains away. So because the water pressure is decreasing as the volume goes down, that will have an effect of slowing the rate of drainage down as the bath becomes less and less full. So that might affect it too. So there are 2 possible options for you to put down for a valid answer to C. Hopefully now we're warmed up, let's now have a look at the idea of summing a geometric series. So the sum of a geometric series. So what is it and how do we do it? So for a geometric series, what we're going to have is the sum of the first n terms of the geometric series, for sum to n, s subscript n, with first term a and common ratio r is defined as the following. So there's 2 different forms of this equation. So hopefully you'll see that each is equivalent to each other. For example, if I take this one here and multiply top and bottom by -1, then it just switches the sign of the denominator, so 1 minus r becomes r minus 1. And if I multiply this by -1, then I can just switch the sign of what's in the brackets. So 1 becomes -1 minus rn becomes positive rn. So both these forms are equivalent and have different benefits. But essentially, if you just remember or use one, you can use the other. So only one needs to be known. So I've told you this, but obviously it would be slightly rude if I didn't prove to you that this is the case. And in fact, you need to know how to prove this result. So let's have a look at how you'd prove this particular result for some of the first n terms is this. So you've got this table here, and like I've said now, this is an absolute must learn. So first of all, I'm going to write the sum of the first n terms like so. So the first term's a, second term is AR, and we keep multiplying through by r, so the next one's going to be AR squared, plus, and so on, and so on. Then over here, we're going to get to the point where it's AR to the power n minus 3, plus AR to the power n minus 2, and of course, the nth term of a geometric sequence is AR to the power n minus 1. Now, the trick I'm going to employ here is to multiply both sides of this by r. So if I multiply both sides by r, so I'm going to times everything on the left by r. So over here, I'm going to have r multiplied by the sum of the first n terms. And over here, I'm just going to have everything multiplied by r. So a times r is AR. AR multiplied by another r is AR squared. AR squared multiplied by another r is AR cubed. And so on and so on. Here, AR to the n minus 3 multiplied by an extra n will give us AR to the power n minus 2. Similarly, over here, we're going to have AR to the n minus 1. And finally, we're going to end up with AR to the power n. So that's how I go from the first row to the next. Now what we're going to do is the top minus the bottom. So top row minus the bottom row. So if we do that, on the left we'll have Sn minus r lots of Sn. And here, with these terms, we'll have lots and lots of cancelling. So, for example, AR minus that AR will cancel. AR squared minus this AR squared will cancel. And so on and so on. AR cubed will cancel with 1 along here. So it's going to cancel diagonally. So AR to the n minus 3, that'll cancel something down here. AR to the n minus 2 cancels this AR to the n minus 2, and AR to the n minus 1 will cancel with this AR to the n minus 1. So we're only going to be left with two things. This A has nothing down here to cancel it with. There's no A term on its own down below. So this A will remain, and this AR to the n will also remain because there's no AR to the n term above, which will cancel it off. So we're going to be left with these two terms. We're going to have A on the top. Sorry. On the bottom, because of subtracting the bottom, it's going to be minus AR to the n. Now, if we look at the left and right, we can factorize both sides. On the left, there's an Sn term in each, so I can factorize out S to the n. So S to the n, brackets 1 minus r. Over here, I can factorize out an A. So A, brackets 1 minus r to the n. And finally, if I divide both sides here by 1 minus r, I can see that therefore S to the n equals A, brackets 1 minus r to the n, all divided by 1 minus r, which is the result we wanted to prove all along. Now, this second result could have been proven if I'd have wrote these in a different order. If I'd have put this bottom row at the top and the top row at the bottom, and then done one minus the other, I would have ended up with this result as well. So if you're not convinced, try it yourself, just switch the order of these rows and it will work. Or, if not, if you don't want to, just try and convince yourself by multiplying the numerator and denominator of this result by minus 1, and we'll arrive at this equivalent form. But ultimately, we've proven here that S to the n is this expression, which is what we've just got here by doing this. And this result is a must learn. They could ask you in the exam to prove this, and you can use this strategy, set it out like so. You can have all these cancellations. As long as you set it out clearly, the examiner can be convinced that you know that many of these terms will cancel, leaving only these two terms that don't, if then factorised, as you can see here, to arrive at what we needed. So now we've got the result, let's use it with some worked examples. So, worked example 1. Find the sum of the first 10 terms of this following series. 2 plus 6 plus 18 plus 54, and so on and so on. So, what's happening here is we know the first term is 2, and the common ratio we can work out by taking one term and dividing it by the one that comes before it. So 6 divided by 2 equals 3. We then need to remind ourselves of that result we just found. So Sn is going to be A, brackets Rn minus 1, all divided by R minus 1. So let's just use this result here. And we want the first 10 terms, so our n is going to be 10. So using these two pieces of information, we can then say that S10, for sum of the first 10, is A, which we know is 2, brackets, R. Now we worked out R as well, so R in our case is 3. So that's going to be 3 to the power 10 minus 1. All of which divided by R minus 1, which is 3 minus 1. So all we're doing here is just using the formula and chucking in the correct values into it. We're not doing anything fancy, we're just using what we proved earlier. So common ratio is 3. In our case, what were some of the first 10 terms? So that's 10. So plug that into a calculator and we're good to go. So we've got 2, then brackets, 3 to the power 10, minus 1, close brackets, all over 3 minus 1. Press equals, we get 59,048. And that is the sum of the first 10 terms. However, what I want to show you now is a way we can use this class whiz to help us do it using a different strategy. So how would you do it using a calculator? Well, again, what we'd have to realise is what A and R are. So A is 2, like I mentioned before, and R is 3. And we need now to go back to what we did in the previous lesson and think what the nth term is. So the nth term of any geometric expression, U subscript n, that's going to be the common ratio, the first term, which is 2, multiplied by the common ratio to the power n minus 1. So remember, we're using this. Un is AR to the n minus 1. This is a totally different way of doing it. You don't need to know this way, but I'm going to mention it because it might well be useful. So in our case, our A, our first term is 2, and our common ratio is 3. And we want our n to be 10. So the sum of the first 10 terms, we can use a calculator like so. So what we're going to do here is we press Shift and then X to get the sigma notation here, which I'm going to make bigger so you can see it clearly. Sigma means sum, and we're going to have a lesson on this notation in its own right, but it can't hurt to just give you a bit of extra information now in advance. So the first 10 terms means we want the first value, so x being 1, x stands for n in the calculator's case, so instead of n, the calculator thinks of it as an x. We want the sum from 1, the first term, up to 2, 3, 4, 5, 6, 7, 8, all the way up to 10. So that means the sum of everything from x being 1 up to x being 10. Now the sequence we've got, if I can just go on and, there we go, is 2 multiplied by 3 to the power of n minus 1, but like I say, in the calculator's brain, the n is x, so type in x minus 1. So where you see an n, calculator just thinks of it as an x. This means the sum of the first 10 terms of 2 times 3 to the x minus 1. Press equals, and the calculator will sum this for you and give you 59,048. So this is a very powerful function on the calculator, which can, at the very least, help you to double check very quickly your answers to questions on arithmetic or geometric sequences or series. Let's have a look now at question 2. Find the least value of n such that the sum of 1000 plus 800 plus 640 plus 512 so on and so on exceeds 4950. Again, we need to work out what a is and r is. The first term, dead easy, you can just see it, a is 1000. So just fill that in, because that's an easy one to do. Common ratio, take one term, I'll take 800, and divide it by the term that comes before it. So 800 divided by 1000, r is 0.8. Now just remind you again of the formula for the sum of the first n terms. We've got Sn equals the first term, then brackets. This time I'm going to do Rn minus 1, all divided by R minus 1. So in our case now, we don't know what n is. We're trying to solve for n, but we do know that a is 1000, and we know that the common ratio is 0.8. So we want this Sn to be at least 4950. So therefore, we want a, which is 1000, brackets, 0.8 to power n minus 1, all over r minus 1, so over 0.8 minus 1, and that to be at least 4950. So now what we can do is go forward and try and solve this step by step. So, at the bottom, 0.8 minus 1, that's going to be minus 0.2. So what we can do here is multiply both sides of this equation by minus 0.2. Just multiply by the bottom number of this fraction, essentially. So what we're going to have here is 1000, and brackets, 0.8 n minus 1. Now, if we multiply an inequality by a negative, what we need to remember is this inequality symbol will switch sides. So it'll become this way instead. So 4950 multiplied by minus 0.2 gives us minus 990. What we can now do is we can divide both sides by minus 1000. Sorry, just by 1000. So 0.8 n minus 1 has to be less than minus 990 divided by 1000. Let's try that. That gives us minus 0.99. Add 1 to both sides. We want 0.8n to be less than minus 0.99 plus 1. Again, use your calculator if you're not sure. Gives us 0.01. Now it looks like we've got a problem, but actually we need to just remember logs. So what we can do here is take logs of both sides. So take logs of both sides. My upside down writing is pretty shoddy. That's meant to say take logs of both sides. So we can take logs to any base. I'm going to take natural log, so ln both sides. So ln 0.8 to the n needs to be less than ln of 0.01. Then we need to remember, if you take logs where it's something to a power, we can bring the power to the front. So then we have n times ln 0.8 must be less than ln of 0.01. We now need to isolate n. So what we can do at this stage is we can divide both sides by ln of 0.8. And at this stage we need to be particularly careful. If we do this, divide both sides by ln of 0.8, of course on one side we'll just have n, which is what we want. We want to isolate n so we can solve it. And on the other side, we're going to have ln of 0.01 over ln of 0.8. But I've made this question deliberately just to get you thinking really deeply and be on the lookout for thinking incredibly critically. We're dividing by ln of 0.8. Now, this might be something you've almost forgotten, and it's easy to slip your mind and get complacent, but if you're taking the log of a number, and the value you're taking a log of is smaller than the base of a log, this log value will be negative. This ln means it's got a base of e is about 2.7. 0.8 is less than 2.7, so ln of 0.8 will be a negative value. So if we look here, ln of 0.8 is negative minus 0.22, so we're dividing this inequality by a negative. So you need to remember, when you're dividing or multiplying an inequality by a minus value, this symbol switches, so we actually need to switch this symbol again. So rather than the open end facing to the right, now we switch it so the open end of the inequality symbol is facing towards the left, facing towards the n. So n needs to be greater than this thing here, which we can now work out on the calculator. So ln of 0.01 divided by the natural log of 0.8 gives us 20.63, and so on and so on. We want the smallest value of n. Now n is what term number we're after. It's got to be a whole number. It's got to be a natural number. The smallest natural number satisfying n greater than 20.63 would be 21. That's the next whole number after 20.6 or so. So therefore, the smallest value of n we're after is 21. Now, you might well agree with me here, that was fairly tricky in terms of how questions go, so using the calculator here could be particularly helpful in just checking these harder questions. So here's the calculator class whiz method. So first of all, we need an expression for the nth term, un. For any geometric series, the nth term is the first term multiplied by the common ratio to the power n minus 1. Here we know a is 1,000, the first term is 1,000, common ratio is 0.8. If I take any value and divide it by the one before it, I'd get 0.8. So that's the nth term. A is 1,000 and the common ratio 0.8. So using the class whiz, I can essentially use brute force, trial and error to just test if our value is correct. We might not be able to wholly rely on the calculator for doing the whole question, because the examiner may well insist in the wording of the question to show a clear algebraic method, or to use known results from sequences and series, or some wording like this. So if a wording is in the certain way, it may mean that you can't just give an answer of n, you might need to show some working. If it didn't say that, if it was just simply state n, you might be able to get away with just using your calculator. It's not always the wisest bet, but it's worth a punt, it's worth a gamble, it's worth a go. But at the very, very least, what I can guarantee you is knowing this calculator method is a good way of double checking your answer, if nothing else. So what we do, we type in this expression for the nth term using the X key, because there's no easy way of getting in the n here. So what we're going to do here is press Shift, first of all, Shift, and then X to get this sigma function up. So we want the terms, think of x as being our n, we want from the first term up to our guess. So let's guess, I don't know, maybe 16 terms will be enough. We then type in our expression for the nth term. So 1000 multiplied by 0.8 to the power of n minus 1. So we put x minus 1. Is the first 16 terms enough? Well, press equals. We're not at 4,950 yet, so we need to increase it. Let's try maybe 18. No, getting closer, but still not there. Will 20 terms be enough? 20. Not quite with 20. If you go one higher to 21, we can see that 21 is the smallest value of our x, smallest value of our n, which will get the summation to just exceed 4,950. So the smallest value of the number of terms we need to add up is therefore 21. 20 wasn't quite enough, 21 just about does it. So that's how you do that question, double checking it using the class quiz. Let's now have a look at the final worked example. So number 3, we've got here the first term of the geometric sequence is a, and the common ratio is root 5. Show that the sum of the first 6 terms is 31a brackets 1 plus root 5. So what we do here is just need to remember what the sum of the first n terms is. So Sn is a brackets 1 minus Rn over 1 minus R. Or, just to remind you of both ways, we could use Sn equals a brackets Rn minus 1 all over R minus 1. So which way you want to pick, it doesn't particularly matter in this case. I'm going to suggest we go for this one here. So what are we told here? Well, the only thing we're told really is that the common ratio is 0.5. Sorry, square root of 5. And we're told that S of 6, well, we need to show that S6 is this. So if we take this and sub in that n is 6, we see that the sum of the 6 terms that first appear will be the first term a, then 1 minus root 5 to the power 6 all over 1 minus root 5. Now, because this is a show that type of question, I'm going to show every single step to make it perfectly clear. I think it'd be very dodgy to just type this into the calculator and just write the next line equals this, so I've proven it. Let's just show it very clearly, step by step. The first thing we're going to do is rewrite the square root of 5. I'll explain why. So I've got a brackets. The square root of a number is the same as that value to the power of a half. So that's 5 to the half to the power 6 all over 1 minus root 5. I'm just doing this to try and make it clear, going back to GCSE even. The power of a power, we multiply the powers. So 5 to the half, the square root of 5 to the power 6 will be 5 to the power of a half times 6, 5 cubed. So next line, I can say this is a brackets 1 minus 125, because 5 cubed is 125, all over 1 minus the square root of 5. Need a bit more space. So next, 1 minus 125 is minus 124. So I've got minus 124a all over 1 minus the square root of 5. I now need to rationalise the denominator. The way we do this is we multiply both top and bottom by pretty much the same thing here, but we just switch this symbol. If that were a plus, we change it to a minus. If it's a minus, we change it to a plus. So multiply top and bottom by this. So on top, we can have minus 124a multiplied by 1 plus root 5. On the bottom, we've got a difference of 2 squares. So 1 times 1 is 1. Root 5 times minus root 5 is minus 5. So minus 124, this becomes minus 4. Minus divided by minus gives us a plus. And in fact, at this stage, we can pretty much just go straight to this. So we're going to be left with 31 minus 124 divided by this gives us 31. Then a, in brackets, 1 plus root 5, which is exactly what we wanted to prove here. And so that'll do us for now. Thank you very much. That's enough of me going on. I want you to try some of these questions yourselves so that you find them fairly okay, not confusing, and you become less and less intimidated by them the more skilled and practiced you've become by doing such questions. What I'm suggesting is you turn to page 72, exercise 3D, and try, as a minimum, these questions. So question 1, A, C, E, question 3, question 4, then question 7, 8, 9, 10, and 11. Check your answers regularly. If you're getting stuck, ask a classmate you trust. If one of those doesn't exist or isn't to hand, then please ask me either in class, on an email, or even in the comment section on this video if you get particularly desperate. Please consider giving me a like, please consider subscribing. Thank you for listening, it is appreciated, and take care till next time. So once again, I'm going to bid you goodbye for now. Take care.